Yeah. So hello everyone. Welcome to week 11 live session of CS47, uh, the blockchain and its applications. Right. So someone was asking a question. Can you? Okay. So please mail them. Like you mentioned that number of exchanges, all the above are one, two, or three, right?
Yes,
Uh,
sir.
you please mail them those I guess like two or three questions in assignment 1, 3 and 5, something like that students have flagged in the
Yeah.
discussion forum.
Yes,
So
sir.
I suggest you mail NPTEL team. They will definitely take action and add marks, uh, update the marks. So
Okay,
try
sir.
to do it before the NSEM exam.
Okay, sir.
They will definitely reply.
Okay, sir.
I'm pretty sure. um,
Okay.
okay, so yeah.
Thank you, sir. Thank you. Pleasantly listened and answered all my questions. Thank you very much.
My pleasure. Thank you. Right. So, any other doubts from anyone else? Okay. So, in that case, what I can do is I'll explain a small concept regarding. So, if you have gone through this week and the previous week lectures, there is a concept called front running attack, and there's a concept like front running attack. So I'll explain this this concept of front running attack again. Okay. So what's the front running attack? Okay. So usually how your transactions are added to a block. Say you're a person and you want to send a transaction, say transaction 1 of 10 bitcoins from Akshay to Ganesh. Okay. So it's like 10 bitcoins means um, Akshay to Ganesh 10 bitcoins. So you pass this transaction to a miner, and the miner will receive like thousands of transactions, and it's up to the miner to in each block. Okay, so in say in block 100, the miner is mining means he will at most based on the block size limit, say 2 MB or 1 MB, something like that. He will include a maximum of 1,000 or 10,000 transactions based on the size of the transactions and all those things. Okay, but the miner is actually what's the reward he gets, right? He gets two rewards. One is the mining reward, which is like the 12.5 bitcoins and all those the new bitcoins which are mined, right, which are created when a block gets added. That's one reward that the miner gets. And the other important reward, which is currently like downplayed, but in the future when the bitcoin total number of bitcoins whatever is hard coded gets mined, and no more bitcoins can be mined, right? So the transaction fees is the important one to be the transaction fees which is being paid to the miner by all the uh, all the owners who are sending the transaction, right? The transaction fees is the second important revenue to the miner. Okay. So this 12.5 bitcoin is constant, and the this transaction fees, the miner will try to select the transactions. Say out of these like say 10,000 transactions which a miner has received, he will try to select the 1,000 transactions having the most um, uh, like a higher fees, right, which he will by adding those 1,000 transactions with high fees, he will get more profit because he's spending so much of resources for mining and all those things. And so say I'm sending a transaction with a fee of just 1 bitcoin means If some other transaction is there with fees of like 2 bitcoins and 3 bitcoins, transaction 2 and transaction 3, then the probability of transaction 2 and 3 getting included in the block would be more compared to transaction 1 getting included in the block. Okay, so this is what the general notion of transactions and how they are added in a block. And what happens is, in a front running attack, suppose say you have a quiz game, okay, and where um, a transaction, say Akshay and Ganesh are two participants. Okay, so Akshay and Ganesh are two participants in the um, quiz. Um, are two participants in the quiz game. And now, say one question is like, what's the national animal in India or something like that, and or like what's the national bird? Okay, so Akshay sends a transaction. Okay, so this is like a decentralized quiz game. So it is a decentralized quiz game. Assume that. And how how Akshay and Ganesh participate in this quiz game is, they send out a transaction, uh, okay, to some specific address, like the quiz master address or something like that. And in that they specify the answer. So national bird means Akshay specifies it as peacock and someone specify it as crow or something. Okay, and they send this transaction on the blockchain addressed to the quiz master. And when this gets added into the blockchain, they see that okay, like Akshay is the first one to answer the question, and the correct answer is peacock, so Akshay's transaction is added into the blockchain. Even Ganesh's transaction would be added into the blockchain, but since peacock is the correct answer, Akshay is given the price amount by in bitcoins in a reverse transaction. Okay, so this is the quiz game. Now we will see how front running attack is used. Uh, how it is being used. So say like as we discussed before, like even if Akshay sends a transaction one, say he sends it at 7 p.m. and the transaction fee he specifies is 1 Bitcoin, whereas Ganesh sends two transactions with different transaction fees. Say he sends it at 7:30 p.m. The irrespective of at what time each of them sent, right? The transaction which has a higher gas fees would have higher probability of being included in the block first, um, before the one with the lower transaction fee, irrespective of the time they sent. So the order in which the transactions are included in a block do not um, uh, they do not represent the time at which the transactions were created and submitted to the blockchain. So it is not always the case that transaction created before transaction 2 would be always, that ordering would be preserved in the blockchain. That won't be the case. It depends on the transaction fee. So this thing is being misused. This property in the blockchain, this inherent property will be misused by Ganesh in this quiz game. And how he will misuse is, he will say like Ganesh doesn't know the answer to a specific question. So instead of sending a transaction, okay, he will just he knows that Akshay is going to send the answer to that question, the correct answer. He will wait until Akshay's transaction is submitted to the blockchain. Okay, and this answer, this peacock would be the answer would be in plain text. Okay, so now what Ganesh will do is, he knows Akshay's say he knows Akshay's public address, or he just knows the quizmaster's address to which this transaction is being forwarded, and he gets to know that this is the answer, and he sees that in the transaction which Akshay is giving to is submitting to the blockchain, he has specified a transaction fee of just 1 Bitcoin, whereas the price amount is say 100 Bitcoins or something. if you answer it properly. Now Ganesh, what he will do is, after seeing Akshay's transaction, he will create a new transaction. So he will create a new transaction with three bitcoins as the fees, and he will copy Akshay's answer. Okay, and he will add the fill up all the details. And, sorry, he will fill up all the details. Okay, and forward it to the blockchain. Now, a miner, what he will do is, when he receives this transaction first, um, this specific transaction 1 and transaction 2. So both he receives, but the miner, what he will do is, he will include this transaction first, which is having 3 bitcoin fees. And since this is being included first, right, the quizmaster will see that, okay, Ganesh is the first one to answer it correctly, and Ganesh will receive the 100 bitcoin cash prize. Okay, so in that case, what's the solution to this? Akshay should either somehow encrypt this specific message peacock over here. He should encrypt this message, or he should add a higher uh, transaction fees to the transaction, say 3 bitcoin or 4 bitcoin. But there is a limit to how much the transaction fees can go, and beyond which, like, it becomes uneconomical to send transactions on the blockchain network. So this front running attack is sort of uh, difficult to control, but in specific applications there are other solutions other than increasing the transaction fees. So in this quiz game, we have this problem. In Ethereum, there is also something called the concept of auctions. Okay, so what they do is usually, like, in the same way, right? How auctions happen in the real world in offline mode, decentralized auctions can occur in. It's possible in Ethereum, and how they achieve this is, so in real world auction, what happens? You have the item which is like auctioned off, and say some base price is 3K dollars or something, right? And there'll be multiple participants. Um and each participant would be raising the auction amount, and the highest bidder would get the item first. So say he tells like 4K dollars, and this guy tells like 3.5K dollars, means this person will get the item. Okay, now if I want to perform this in a decentralized manner, as in like a fully decentralized online way, via these smart contracts and transactions on the Ethereum network or the Bitcoin network, how can it be done? Now, similar to how the quiz game works, say you have to send a transaction where you specify the tender amount, say like 4,000, like $4,000 mean like 4 bitcoins or like 1 bitcoin. You specify that amount, and then you specify the address to which you have to send it. Okay, so say like person one sends person one sends this to the auction address, and similar to this front running attack, what will happen is some other person, he will scan all the transactions having the destination address as the auction address, and what he will see is this 4 bitcoins is the auction value, and a malicious attacker, right, he will create a new transaction and specify just 4.001 bitcoin, and he'll send it to the address, and he will just add a higher gas fee, or he need not add the gas fee, he need not increase the gas fee also, because this is sort of in excuse me, so it is sort of in plain text, and the auction rules is the one with the higher amount wins the auction. So just like with 0.001 bitcoins extra, the attacker can win the auction, right, and get hold of the item. Like, right. So to avoid all this, there is a concept which I won't be going too deeply. I'll just introduce to you. So there's something called as oops, something called as submarine sense. I'm submarine messages, something like this. Okay. So the idea is, instead of sending these amounts in plain text as part of the transaction, you should perform some encryption. Okay. So basically you perform some encryption on this amount so that an attacker cannot directly see what amount you are specifying in the transaction. He cannot infer what amount you are quoting as for the auction, and so he won't be able to guess. But now a problem with this aspect is, say since you are encrypting the amount, right? Um, the key would be like sort of shared with the auction entity. But since you're encrypting your identity, you're not revealing your identity and all these things. There might be a case where say just to disturb the auction, the attacker might just say like 12,000 bitcoins I'm quoting. But since the attacker's identity is not revealed, right, it might be sort of a denial of service attack or something like that. Okay, so there should be a way to connect the identity of the person with respect to a specific transaction, and at the same time others should not be able to associate that person with this transaction. So submarine messages sort of cleverly use a set of transactions. Their trick is, they, instead of sending just one transaction, they send like 12 to 13 transactions, a group of transactions, so that they confuse the attacker, and the attacker cannot infer the identity of the person, as well as they cannot infer the identity of the uh, they cannot infer the amount that is being quoted. And at the same time, it is easy for it's designed in such a way that at a later stage it would be easy for the when the auction is closed, the auction organization, they can easily go through all the amounts that are which are being quoted, and find out the winner, and reveal the winner identity and all those things. So this is sort of like why I explain this is it's sort of relevant to this front running attacks, and the protocol or the technique they used to um, design these sort of auctions in a decentralized way is called as submarine sense or submarine messages. Submarine sense, because just like how you send like multiple submarines, you don't like send one submarine. It's like the messages are all hidden from the attacker, and finally when the auction is over and at the correct time those messages are revealed. So in the same way, how a submarine, like if it has to attack or something, right, like it has to come up, and the way it works, these message passing and all those things mimic the type of the submarines. So they name it such a way, and it would be an interesting read. And these techniques were founded to prevent these type of front running attacks and all those things, and make it viable to conduct these type of financial services in a decentralized way on the blockchain. So usually these type of financial services like quiz game or something used to be like an offline mode, or like if even if it's in an online mode, it will be in a like a centralized way, right? You will reveal your identity, and then um, uh, you directly communicate with the quiz master and all those things. But this sort of like if you want to mimic this in a decentralized way, you have to try to infuse some ordering on the transactions, which is difficult in the presence of front running attacks. So these are some techniques which are being used. Okay, and similar to this front running attack. So in front running attack, usually the so usually like the attacker will try to um, try to tries to intercept a transaction, and send that transaction, the attacker's transaction A, with a higher gas fees, right? With a higher gas fees such that transaction A is included first. So this is what the front running attack is. Okay, there is something called as the sandwich attack. So in this, what happens is, say um, some person, Ganesh, sends, say, transaction 1. What the attacker will do is, he will include two transactions. So this transaction 1, what he will do is, he will say this is having 1 Bitcoin as the gas fees. Okay, and what the attacker will do is, he will include transaction A1, which is having 2 Bitcoin as gas fees, and transaction A2 is having zero point 0.5 Bitcoin as gas fees. Okay, so notice he will include two transactions such that transaction A1, one transaction will be included in the blockchain, in the block before transaction 1, and one transaction released by the other transaction released by the attacker would be included after transaction 1. So it's sort of like a sandwich. The actual transaction 1 is sandwiched between these two attacker transactions. And what will happen in this case? What's the big deal about this? You can think. Uh, there is something called as, like, for example, decentralized finance, which is popular in the blockchain world, especially these public blockchains. Okay, so DeFi. So in this, so basically, when we say Ethereum, right? ETH, Ether tokens. There are so many other tokens based on the Ethereum platform, which are compatible with Ethereum, right? So they are all like ERC22. There's a So these are all, like, they call it as fungible tokens, okay? And all these tokens follow this ERC22 standard. And the cool thing is, say all these, so there are like hundreds of tokens, okay? And they all have a value, like, say for example, 1 meter is, say, $30,000 means, some other token, for example, like, there is this, I guess, USDT, or Tether. I'm not sure of the names actually. So these are actually, one USDT is like a token similar to Ethereum, but it is pegged with the US dollar. So the value is one USDT is one US dollar always. It's 1 US dollar. So there is a platform called Uniswap. And what Uniswap does is, it is sort of how you go to a foreign exchange to exchange, say, Indian rupees and US dollars or any foreign currency, right? Um, in the same way, Uniswap is sort of a decentralized exchange for um, decentralized exchange for these tokens. Okay, so say I have some meters. I have 20 ethers. I want to get an equivalent amount of another token called USDTs, something like that. Okay, so 20 ethers. So 1 ether, say it is um, 2000 USDTs. Okay, and so 20 ethers I'll be getting 40,000 USDTs. Okay. And how this price in Uniswap is maintained is, how it is decided is the same, like every day, say, like 1 Indian rupee, 1 INR is say like 70 US dollars, something like that. Okay, so that will be the current rate in currently at this time. If you see the next day or even like after an hour, or like it will keep on changing, right? So now it will be like 71, or it will be 69, or it will be 70.5. It will keep on changing. And how this keeps on changing is based on supply and the demand, right? If there is more demand for Indian rupee, as in like if more US dollars are converted into Indian rupee, so the demand for Indian rupee goes up. So the price of the Indian rupee goes up. So initially, if it say one Indian rupee is 70 US dollars, now it will be like one Indian rupee is more. As in it will no, sorry, it will be the opposite, right? So the price of Indian rupee will go up, means so one Indian rupee is uh, sorry, got confused. So so US dollars are converted into, so the value of US dollars will come down if the demand for Indian rupees is more. And so it is sort of um, okay, this the opposite actually I wrote. We'll change this. Sorry. So 1 US dollars is 70 rupees, right? So 1 US dollars is 70 rupees, means now if US dollars, more US dollars are being converted into Indian rupees, then the value of Indian rupees will go up. So with less Indian rupees, you can equivalently buy like the 1 US dollar. So like it will be like initially if it say like 1 US dollar is 70 rupees, means if the demand for Indian rupees is more, e- um, you can easily the value of converting INR to US dollars would be less compared to the value compare like converting US dollars to Indian rupee. So say initially it was like 1 US dollar is 70 rupees, means if the INR value goes up, it will be now like 1 US dollar is um, 68 rupees or something, right? The thing is the value of US, since Indian rupees is more in demand, if I want to um, get the same 70 rupees, means I should, instead of spending 1 US dollar, I should be spending 1.2 US dollar. So I should be spending more to get that same amount of Indian rupees if the demand for Indian rupees is more. So this is how your normal foreign exchanges work in any country around the world. So now in Uniswap, which is a decentralized exchange, say if I want to convert some Ethereum, some Ether tokens into USDTs. Okay, so based on the current demand, okay, so that Uniswap platform would be maintaining the number of uh, users who are converting from Ethereum to USDT and vice versa. So they'll be based on the demand, right? The price of conversion, okay, the exchange rate to be specific. The exchange rate varies. Okay, so say now if we look at this example over here, this transaction one, say Ganesh is sending a transaction, he wants to convert. Um, so say he wants to, he assumes that he wants to get some USDTs. Okay, so now say one Ethereum is sending one Ethereum, and he wants to get some USDTs, and say currently when Ganesh is submitting this transaction one, with one Ethereum he is able to get 2000 USDTs. Let's assume this. Okay, now what happens is when Ganesh sends this transaction one, the attacker sees that okay, Ganesh is sending it to the Uniswap platform. The address is known to Ganesh, to the attacker previously, and the attacker can infer from the transaction that Okay, Ganesh is sending one Ethereum and he somehow infers that he wants to exchange that ethers for USDTs. Okay, now what the attacker can do is he can send two transactions, one with a higher gas fees and one with a lower gas fee with respect to transaction 1, such that this transaction A1, what it will do is it will increase the demand for USDTs. Okay, so what he will do is he will try to um, so say he wants to um, so the okay, so say now like so Ganesh is swapping swapping ETH for USDTs. So Ganesh wants USDTs instead of ETH. Okay. The attacker's aim is to send a transaction before and after transaction 1, such that instead of Ganesh acquiring 2000 USDTs based on the current exchange rate, Ganesh should receive less number of USDTs. How is that possible is the Uniswap, the exchange rate varies with each transaction, as in like based on the demand it will keep on changing in Uniswap. So if the demand for USDT increases, okay, the demand for USDT if it increases, then instead of um, giving back 2000 USDTs for one ETH, Ganesh will receive only uh, say like less number of USDTs instead of 2000. Say so now what the attacker will do is he will send a transaction A1 with a higher gas fees, specifying if I want demand to for the demand for USDTs to increase, he will send out a transaction specifying um, uh, um, so he will send out a transaction, let's say um, he will send out like two uh, say two ETH or something. Okay, so now what happens is for 2 ETH the attacker would get like 4000 USDTs. Okay, and what happens is now actually the demand for USDT increases because see like previously 1 ETH equals like 2000 USDTs, but now more and more people say this attacker he sends out transaction in such a way that the Uniswap protocol, the algorithm will assume that by seeing these transactions, people or the consumers are more interested in getting USDTs. Okay, and since the demand for USDT has increased, right, the what the Uniswap exchange protocol does is it will increase the price of USDTs. So with that same one ether token you will receive, instead of 2000 USDs, you will receive just 1900 USDTs. So the demand for USDT increases, and now when transaction 1 is submitted, right, so for one ETH, if Ganesh assumed he will get 2000 USDTs, he just receives um, uh, say 1900 USDTs. So the attacker, what he did is insert after transaction 1 is submitted, now he will submit transaction A2, and in transaction A2 what he will do is he will just do the opposite. The opposite is nothing but whatever USDTs he received, right, this 4000 USDTs in transaction A1, he will pass it to over here and he will exchange it for ethers. Since the price of ethers has come down, right, since like USDT to ether, it's sort of uh, the demand for USDT is more. When you get back ethers, it will be sort of you will receive more ethers, right? So for example, um, At the time when transaction A1 executed with 2 ethers, you are able to get 4000 USDTs. Okay, so this increased the demand for USDT. When transaction 1 executed, the demand for USDT still increased, and what happened? For 1 ether, instead of receiving 2000 USDT, you received 1900 USDT. Okay, now see the value. So if you are giving 4000 USDTs at this stage, let me just use this. So if you are giving 4000 USDTs, how many number of ethers based on this value, based on this transaction, this exchange rate you will get? So 19,000 into like 2 ethers, so something like 2.2 ethers you will receive back. So basically what the attacker is aiming for is he should get an increase in the uh, he should he should he should get a profit finally. That's the aim of the attacker. And in this Uniswap protocol, similar to a foreign exchange, based on whatever transactions they receive, the Uniswap exchange receives, the demand, the exchange rate for a pair of tokens is determined. It will vary based on, say, a set of 10 transactions or something. And um, it's something like uh, so when Ganesh, valid user who really wants to exchange some ethers for USDTs, he sends out a transaction expecting he will receive 2000 USDTs back. But the attacker tries to infer that information, and what he does is he sandwiches that transaction 1 with his 2 transactions such a way that he increases the demand for USDTs before Ganesh's transaction executes, such that Ganesh is at a loss, whereas the attacker later, on receiving those 4000 USDTs, when he executes transaction A2, when he receives back the corresponding ethers again from the Uniswap exchange, he receives higher number of ethers. So if you notice over here, the attacker sends out just 2 ethers and receives back 4000 USDTs in the first transaction, which increases the demand and makes Ganesh transaction a loss, because instead of receiving 2000 he received just 1900. Now the attacker, if he gives out this 4000 USDTs in the transaction A2, and if he wants to receive back some ethers, instead of receiving 2 ethers, you notice that since the value of USDTs has increased due to transaction A1 and this transaction 1, the attacker receives back 2.2 ethers instead of just 2 ethers. So there is a profit of zero point 0.2 ethers, which the attacker didn't do anything, like he just increased the gas fees a little bit or something more than transaction 1, but he got zero point 0.2 ethers for free, right? So this is sort of profit for the attacker. So this is called as the sandwich attack. So similar to front running attack, a sandwich attack, instead of just sending one transaction, you sandwich the transaction, the victim transaction, between the attacker transactions and send it to the blockchain, such that this is the order in which you include the transactions in the blockchain. And this type of sandwich attack is very predominant in platforms such as Uniswap, where you want to exchange between tokens in a decentralized way. Okay, so this is called as the sandwich attack. And Uniswap, they have upgraded their protocol such that, say, instead of they call something called as the slippage model, as in um, so the things with the beauty with all these decentralized exchanges, right? They share a lot of ideas with the financial domain, and they try to incorporate those ideas into these decentralized blockchains. And the slippage cost, say, like instead of in the problem with these set of these three transactions is that Just by looking at transaction A1 and this transaction 1, the value of USDTs increased a lot. So instead of looking at just two transactions or something, or just blindly increasing the value of USDTs, the protocol was changed in such a way that the value of any token based, even if its demand increases suddenly, right, even if it spikes suddenly, the the exchange rate does not arbitrarily change to some high value suddenly, but instead it will change step by step in a limited fashion, so that even if the attacker tries to mount these sandwich attacks, finally after that second transaction, what the attacker does, right, transaction A2, the profit he receives will be relative significantly less and not very high. So they limit the profit which is gained from these sandwich attacks, and that is a deterrent for these type of attacks to be staged in real world these decentralized exchanges. Okay, so these are the two types of like front running attacks. Usually they rely on changing the gas fees and all those stuff. Okay, and yeah, um, so this information I wanted to share. And the other thing is in uh, the other aspect, an interesting um, um, I came across this article, right? So uh, wait, what is the article? One second. Selfish. Okay. So I guess Sir Professor in the lectures would have discussed about selfish mining, right? So where you have say a private mining pool, and this private mining pool will have set of nodes, and say it represents 10% hash power, and some transactions are submitted to these mining pools. Okay, these private mining pools. Now instead of um, interacting with the other miner nodes, and instead of wasting their bandwidth and wasting time in communicating with the other miner nodes, right, these private mining pools having 10% of the hashing power, what they can do is they can try to mine between themselves, and they will increase with, since they are not interacting with the other miner nodes, right, they save a lot of time with respect to this intel node communication and all these things. And what happens is their block creation is much faster, and at some particular time, say the general blockchain is at block 100, means like 100 blocks have been added, and this is like block 100 is the latest node, means these private mining pools, since they are not interacting with each other, they save a lot of time, and they will eventually add 5 more blocks or something like that. Now what happens is the other 90% of the mining nodes and all those things, they will be their mining power would be segregated, as in each node would just be contributing zero point 0.5 of the hash power, something like that. And um, collectively they are not working on the same block, everyone would be working on different block, and there will be a collision, and there will be forks, and they'll be resolving those forks, and say they were able to reach till height 102, but these mining pool they were able to reach till height 105. When this is the case, when this occurs, what the mining pool will then do is the selfish mining strategy. They will release this set of 5 blocks to all the nodes. Now they will release the set of blocks which they have mined. Now when all the nodes receive these 5 blocks on top of block 100, the height is 105, and compared to their current block height which is 102, they will all the other miner nodes not part of the mining pool will believe that these nodes, these blocks are the correct ones. We had been in the dark, and they will accept the blocks part of this 105, uh, these extra 5 blocks. They'll accept it, and they'll discard these 2 blocks. So the blockchain is basically like reorganized, and these 5 blocks are now part of the blockchain instead of these 2 blocks which were mined by the remaining 90% of the nodes. Okay, so this is what is called as the selfish mining, where the private mining pool or like a set of node, right? They don't interact with um, the all the other miner nodes. They maximize their mining power, and try mining new blocks, and at a particular time when the current block height is less than their which are less than the number of blocks which they had mined and kept it secret from all the other miner nodes. When that is the case, at that time they will release their blocks so that their blocks get included in the blockchain for sure, and like it's sort of they get more reward. The probability of the reward is more, and the probability of their block getting inserted into the blockchain is more, because instead of like proposing 1 block at a time, if you propose 10 blocks, right, definitely those 10 blocks should be added, because those 10 blocks add credibility, because like all those blocks are chained together with each other, and they represent more hash power and hash rate. And those 10 blocks, when they are added, your block height increases by 10 instead of just by 1, and they're sure to be added. But this thought of selfish mining is discouraged in the network, because discouraged in the network because finally this might the essence of a blockchain, the security of a blockchain, relies on the fact that no individual pool or a node can, like the mining pool or node, can control your blockchain. They cannot control the blocks which are being added to the blockchain deterministically. But now with selfish mining, even with less than 40% of the hash power, they'll be able to control what blocks are added into the blockchain. So it's basically like sort of a monopoly in this mining area, where if you are part of this mining pool, then you get more rewards, or if you want to act independently, you don't get rewards. So all these again centralization issues and all these things come into picture, and it loses the essence of having a decentralized blockchain. Now, so selfish mining is usually discouraged, but now there is a situation like, where in 2015, 16, I'm not sure of the date. Okay, so what happened? The story goes like this: some smart contract which is used to send out tokens to users which interact with the smart contract had a bug in it. The bug was such that if a user who interacts with the smart contract wants to delete his account or something, the smart contract, what it will do is, the bug was, instead of just deleting the user's account, it will transfer all the tokens, the ETH tokens it has in its control, to the user who is deleting his account. Something like that, some logic similar to this. Okay, and at that time the smart contract had ETH tokens worth 9.6 million US dollars, which is a pretty high amount. Okay, 9.6 million US dollars. So the smart contract has to be upgraded. It can be upgraded easily by sending out a transaction on the blockchain with an updated code. Okay, but there are two issues. One, if we send out a transaction on the blockchain with the upgrade to the smart contract with the bug being removed, there is a possibility of front running attack. As in, say a malicious miner who gets this transaction, he gets to know that okay, they are updating a smart contract. He gets to know, the miner gets to know, and uh, if the miner is able to find out that the update is with respect to this specific bug, and if we exploit this bug we get 9.6 million US dollars, then what the miner or any attacker they'll try to do is they will try to uh, prevent this transaction from entering the blockchain in the first place. They will try to exploit the bug, get the 9.6 million US dollars, and then include this transaction in the blockchain. Okay, so this the when you're upgrading your smart contract, it is public. It's made public to everyone. The transaction is made public. But here is a case where the upgradation should be done secretly, and only when it is definitely added into the blockchain for sure. When it is added into the blockchain means your smart contract is updated for sure, and only in that case your smart contract is saved from this bug. So in this case what the developers did is they resorted to selfish mining to prevent this sort of front running attack, because usually in front running attack the solution is if you increase your transaction fees, then the probability of this transaction being included is better. But here 9.6 million US dollars is quite a big amount, and if any minor node or anyone gets to know of this bug, they can easily try to say like send a transaction fee as 1 million US dollars. And even if they spend 1 million US dollars as transaction fee, in return for profit they will be getting 8 million US dollars. It's a huge amount, right? So here in this case, for upgradation to the smart contract, they did a selfish mining where they provided this transaction to a private mining pool who they had confidence with that he wouldn't misuse this bug. This private mining pool included this transaction in a block for sure, and then when the block height which they have been which they have been working on in a private way was more than the current block height, right? Then they released all those blocks to the other miner nodes, and based on the selfish mining strategy, these blocks 100 and 100 and 102 or these things were all deleted, and the nodes and the blocks which were released by this private mining pool was included in the blockchain. So before the transaction or the upgradation was made public, due, using the selfish mining strategy or this private mining strategy, they were able to confirm that their transaction was included in the blockchain and not exploited by the attacker. So this is sort of like, even if we go against this selfish mining, there are some use cases where this is critical, especially in this security vulnerabilities, bug patching, and all those things. Especially in the way the transactions are not uh, the ordering of the transactions are not deterministic, right? You cannot prevent any other transaction accessing that smart contract before it gets upgraded. The miner node is in full control. So in these cases, selfish mining is sort of used. So this one interesting uh, article I came across and I wanted to share it with you. Okay, right. So any doubts? So this is what I wanted to discuss about in this lecture. Hope you understood the concepts. In tomorrow's lecture, the Saturday session, I'll be discussing about the cross-chain swaps and the other um, topics that the professor has touched in his video lectures. So, any doubts in this specific? Yeah.
Yeah, Sai sir, thank you. I
Yeah.
actually doubt not from this lecture. Earlier lecture, na, I have one or two doubts, sir.
Okay. Which doubt?
Actually, in earlier lecture, na, professor told it for Bitcoin. protocol. So initially it was told that TCP protocol is used. Then in one of the lecture, then again professor told gossip protocol is used in Bitcoin. So either both are used, or what is the difference, sir?
In the first lecture, what was told?
It was told me that TCP protocol is used for in Bitcoin. TCP protocol.
Oh, okay.
Even,
TCP and gossip is it you're telling?
yeah, yeah. So
Oh,
are both
TCP.
same or different, sir?
No, no. So, wait. Okay. TCP is the network stack, the standard actually. I guess like right. It is the standard. So gossip is like sort of how you. So TCP is different. It's like network protocol. Gossip you build it on TCP. Everything uses TCP. Like everything is networks only actually. Gossip is
So,
gossip protocol is the way in which you interact interact with your nodes.
okay. And so any difference, particular any,
No, no.
because
See,
I'm not in that network area. I'm
no,
a electrical engineer, so I cannot understand
no,
any
no. See,
basic difference.
it's you have a browser. Okay.
Yeah,
What does a browser do? You browse the net. You browse
yeah, yeah,
files. What's
yeah.
the difference between Google Chrome and a browser?
Okay, so
Google Chrome
browser,
is a
it is one of
browser,
the part.
one
Yeah,
of the browsers, and
yeah,
it's actually like it has browser functionalities and also more than that. It has like plugins and all those extra things. Same way,
yeah, yeah, yeah.
TCP is the network standard. Like it's
Okay.
and Gossip is somewhat fine tuned for this Bitcoin, like this distributed system. You have nodes present all over the world, right? You will be sending out so many messages, and you want to minimize the overhead, the network latency. So Gossip protocol is sort of such a technique which is being a protocol which is followed in the Bitcoin network.
But one of the question they told TCP protocol also used for Bitcoin. So if suppose question comes in that both are mentioned, TCP also there, gossip is
No,
also
no,
there.
TCP is the underlying technology. Um,
Okay.
Gossip is all like using TCP.
Hmm.
There won't be a question like that.
Okay, okay. Thank you, sir. Thank you.
Okay. Thanks, Shyam. And also, sorry, the last session and like couple of sessions I had to postpone due to some personal reason. Sorry for that.
Yeah, thank you, sir. Thank you. No problem, sir. I
Okay.
will be in contact with you, sir, because I'm working in this area. I'm working on my PhD now. Maybe soon I'll start.
Okay, sure. Nice to hear that. Thanks, Shyam. So, anyone else have any questions? Uh,
One more, sir. I wanted to ask, sir. Sorry, sir, again.
yeah, yeah,
One more thing, na, I wanted to ask. Suppose recently Professor told us this regarding hyperledger and this hyperledger grid and all. Na, so many.
yeah.
So suppose if I want to go for blockchain platform, uh,
Okay.
do you have any contact? How we can get this platform? Like pre and
No,
all I have seen, like remix and all I have seen, but I want for project na. So how shall I go? Do you have any idea, sir?
no, I don't have much idea about the contacts or those things actually with respect to this hyperledger and those things. I don't work in the blockchain field like first hand, but I understand the concept. So, but
Okay, sir. Okay.
okay,
Okay, sir. Thank you.
okay, thank you. Okay, so if no other doubts, then we can end this session. Thank you so much, everyone, for attending the session. Have a happy weekend. Thank you.
Thank you, sir. Thank you.
Yeah, thank you, sir.
Thank you.
Thank you, sir.